Bismillahirrahmanirrahim. رب اشرح لي صدري ويسر لي امري واحلل عقدة من لساني يفقهوا قولي. Today we are going to start our session. I'm session chair Dr. Asif Hafiz, and with me Dr. Muzaffar Mahmood is helping our session. Our first speaker is Dr. Waqas Khan Sayani. He is from University of Kotli Azad Jammu and Kashmir, Pakistan. He has done his Doctor of Philosophy in Biochemistry and Microbiology from Swedish University of Agriculture Sciences. Yes, please, Dr. Waqas, please. Dr. Waqas.
Unmute यहाँ से हो गया चले से.
Thank you.
Yes, Dr. Waqas. Can you hear us?
Hello.
Hello. Yes.
Just a second, please.
Okay.
Could you please tell me where to share the screen?
There is an option at the taskbar. You can see on your presentation that it will start to share your screen. Drag your mouse over to the PowerPoint, and then you will see an option which says Start Sharing.
Okay. Just a second, please.
Okay, take your time.
It's okay.
Help me to find the where to. Where is that one? On the taskbar? Yes.
Yes. Is your presentation open at the moment?
Hello.
Yes. Is your presentation open at the moment?
Yes, that's open.
Drag your cursor over it.
Yeah.
Now you can see. Do you see that option which says Start Sharing? If not, then I will tell you another way.
Yes, please go and tell the other way.
Okay. On the MS Team, you can see the Share Content option right beside the Leave red button.
Right. Yes.
Share. Now click on the Share. And then
share
select the
screen.
you
Yes.
want to share.
Yes.
Thank you.
Yes. Is that visible now?
Just a moment. Yes, it is. Make him a spotlight.
Thank you very much for the inconvenience. My name is Dr. Waqas Khan, and I am an assistant professor at the University of Kotli Azad Jammu and Kashmir. And the title of today's presentation is Eco-Friendly Bioplastics and Transforming Waste into Sustainable Solutions. So, as we know, our group is working on the bio-waste management and to transform those wastes into the products which are used in the daily life. And among them, potato are one of the staple food crop. And according to the United Nations Agriculture Organizations, the global potato production is estimated to be over 368 million metric tons annually. And in the figure here, it is shown that the areas which are marked in the dark gray colors, they are producing higher potatoes, and while the other countries which are lighter in the color, they show least production. And this is basically dependent, also dependent upon the consumption of the potato. So whenever somebody is intending to use potatoes, definitely she has to peel it off. And after peeling potato, the peels, they are really sometimes they are in greater number, and there is some statistics that anticipated potato peel waste into 2030 is approximated to be 8,000 kilotons, and the greenhouse gases emissions is expected to be more than 5 million tons annually. So there are definitely some environmental concerns, like it contributes to the global warming and climate change, and also it destabilizes the ecosystem, impact the water quality, air quality, and other things associated with it. So environmental degradation definitely affects all of us, and there is an urgent need, and many groups of researchers, they are working on the minimization of this problem. So what we thought of using this waste, the bio-based waste, and using this bio-based waste for the production of materials, and have you ever thought that question prompts in the mind that have you ever thought about the hidden potentials of the potato peel? So potato peel composition next is water is in leading amount, almost 85% in the potato peel. After this, the total carbohydrate or starch production, that is almost 7.8%, is present in the potato peel. So we thought that what is the thing which could benefit us, which we could use from this waste. Out of this waste, then we thought that yes, we could go for the starch isolation, and this is really very interesting and very important to get starch, and an easy process also. So next was also the potato proteins, the second one, and potatoes are grown globally, and mainly starch is isolated from the potatoes, and during the starch extraction, the proteins of the potatoes, they are degraded. So when we consider about the industrial production of starch at that moment, the monthly production of proteins is in millions of kilograms. So we decided to, and during the starch extraction, that protein was degraded, and then we thought that yes, we could use this protein. And how we could use this protein? The answer was only that we could use the proteins when they are thermostable and they are not degraded during this starch extraction by the thermal by the heating. So then we thought that yes, what sort of the composition of the protein is there? Normally arginine, tyrosine, and they are on the peripheries, and alanine in the core of the protein. And what are the attributes of temperature intolerant proteins? And they have cysteine and serines in the core. So we decided then to change alanine molecules from the core of the protein, and then adding some of the cysteine or serine. Definitely we cannot change cysteine because this is also giving the mechanical strength of the protein, so that's why that is more thermostable. So we decided to increase the amount of serine molecules in the core of the protein. This we did that the potato proteins of potato, they have a like PAT5 protein or PAT3 protein. They have two adjacent serines at 3 different locations, and then we use CRISPR technology, and by using the CRISPR technology and the alteration of 4 nucleotides, we were able to change 2 serine molecules, 2 adjacent serine molecules from the core of the protein into 2 alanine molecules in the core. So we designed a construct, and they did our transformation, and also given some of the donor templates for the incorporation of our changes into the protein. So the potato variety of Curas that was used, and then we got almost 40 lines with which were having some edits, and then what we thought, what after that we got the degradation test of the proteins after isolation from the potato. We got that 5 degrees centigrade shift in the degradation temperature. So potatoes, they were degraded at 45 degrees centigrade, and that was increased up to 50 degrees centigrade. And now we got some of the proteins which were not degraded, and definitely those proteins in the future were used for the human food, will be used for the human food. At the moment, they are not used for the human food. They are used for the horse feed, because that is also having some sort of glycoalkaloids, and that is having some problem for the digestive tract of human being. So we rescued that one out of the waste, and then focused back on the starch material. So some of the innovative solutions from this starch and protein material that could replace the waste with the valuable values from the waste. So problems with the traditional plastic is, there is this persisting in the environment and not degrading even after 1,000 years, and having some problems, pollution, and then this is the thing which everyone I think know at the moment. So then we thought, yes, we could go and use this starch and this protein material for the production of bioplastics, and that bioplastics would be definitely, because these substances would be bio-based, so we could use them for the production of bio-based biodegradable materials that come from the renewable sources, and we can and can be used to reduce the problems of plastic waste that cause pollution to the environment. And so some of the properties of the bioplastics, that they would be degraded in a certain period of time, and definitely having some almost the same quality, not exactly the same, but we would be tending to modify them for the almost same properties. So then after the extraction of starch that was used with some other materials and potatoes, definitely then they were intended to form some sort of films. So what was the method that was used? First of all, washing of the potato, then drying, peeling of potato, weighing, and then dicing of the potato peels, blending, making a slurry, then its filtration, addition of some water, discarding that supernatant because that was having some sort of impurities, and that was also giving some brown color to that. After subsequent washing, then it was drying, and then we got pure powder that was shown here in the figure beside the potato. Then it was intended to produce the bioplastic films, and then starch water solution was made, and then it was heated with continuous stirring. Then plasticizer like glycerol was added, and the heating was done up to almost 80 degrees centigrade with continuous stirring at almost 2 hours. Then pour it into the petri plates. This is like casting method, and then allowing it to dry, and then peel it off like you can see in the figure. So then next was the characterization of this starch. Here you can see the starch molecules in scanning electron microscopy. Here are some sort of peel starch, and then another biofilm that was made of the infested construct, because grains they are used to eat definitely, and that is the prime importance of them. When the then when the grains they are infested with some sort of like fungal or some other pathogenic attack, then that is definitely not good for the health. So after that, we purchased some of those grains and then isolated some starch out of it, and then produced some of the starch biofilms out of it. You can see both of them. Then done some antibacterial assays, and it was showing some sort of resistance definitely to E. coli strains. After that, antioxidant assays were done, and that was showing yes, they have some sort of antioxidant potential also. And then XRD for the confirmation of the some specific peaks, and then FTIR analysis was done. So later on, this work is going on in the process yet also. So what we intend now is to isolate whatever the good material we could have, we could extract from the waste. Like I have spoken also, I have talked about the infested starch, infested corn starch, and also the infested wheat grains. And then we also intend to isolate some sort of proteins which are sticky in nature from the not only from potato but also from other grains also. And then to isolate this type of material like proteins and starch, and then using them in a blend, and also using some sort of plasticizers with them, along with them to produce biodegradable materials like films, and also for the other materials. And what we intend, we would like to produce some sort of biodegradable plastics which are also edible. So when somebody would buy some product, and they would definitely be used in the packaging industry, then we also intend to that this material would be used for that packing purposes. And then as a whole, when somebody would purchase the material, then they can cook with the packaging also, because that is biodegradable, and also having some like starch and protein composition. So what is our take-home message? Like is that potato peel starch-based bioplastic stands as eco-friendly alternatives with properties rival their synthetic counterparts. Their strength, elasticity, and stiffness make them adaptable to various applications, such as for packaging and high-end applications such as automobile parts. And definitely environmental responsibility. It's our collective responsibility to make sustainable choices and reduce our ecological footprints by supporting and adopting products like starch-based bioplastics. We can also contribute to the healthier planet. And as consumers, let's choose products that align with our environmental values. And as industries, let's prioritize sustainable practices and innovation, and also together with we can build a greener, cleaner, and more sustainable future. Thank you very much, listeners. That's all from my side. If you have any questions, please go ahead.
Thank you very much, Dr. Vikas. We have some follow-up questions. Yes, Dr. Please.
Dear Dr. Vikas, I have a question. Would it be economically feasible to recover a nominal 8% starch in potato peel? Because the technique you have described in your research involves some energy extensive unit operations like filtration, drying, or separation, etc. Don't you think we should be using these potato peel directly as animal fodder rather than using this processing technology to recover only 8% of starch in it?
Thank you very much for such a nice question. Actually, what we intended, because like food and feed, our focus was not for that purpose. this was when we were doing this in the laboratory. We were getting the potato peels and just chopping them with the in the normal house use blenders, and then washing it multiple times and then leaving that into the sun, and that was drying. That was not involving any type of rocket science. That was purely no filtration, because we were doing decantation. Definitely for the production of this much sophisticated biofilms, and then we are going to use the FTIR and checking the peaks and avoiding impurities. So that involves some sort of filtration and other things also. But what we were doing it in to get them in the bulk, that is very simple. Dicing of them, then crushing, like blending them, and then that solution is washed 2, 3, 4 times, and then left over in the environment, under the sun, or maybe in the room under the in shade in air. So that is dried. So it's very simple. And we are also focusing we are also focusing them for the production of some sort of food particles also, but not from the starch. That is intended from the proteins, as I told you earlier.
Thank you,
And
Dr.
also,
Vikas.
some of the environmental footprints, footprint is higher, and more costly of plastics, and sustainable alternatives are now, necessary, and we would like to replace those recalcitrant plastics from the environment by doing this also.
Thank you, Dr. Vikas. Got your point. Thank you very much for the clarification.
Dr. Vikas, I have a further question. Have you done any studies on the biodegradability? How much time does it take for this starch film to degrade?
Actually, we are currently producing them and checking them the biodegradability in the different type of environments. So yes, we have done that, and when we were doing this in the environment, like in normal environment where there is less humidity, and most of the dry environment, it takes like more than 100 days for them to degrade. But it depends upon the climatic conditions. Like if you have lots of humidity, don't have direct sunlight, then they are degraded quite fast. But definitely once they are the products, they are ready, definitely there would be some value additions to avoid some other degradations also.
Thank you very much, Dr. Vikas, for your insight on this on the topic of eco-friendly bioplastics transforming waste into sustainable solutions. It was indeed a very insight for this new area of biodegradability and eco-friendly. It will also help us in the circular economy as well. Thank you, Dr. Vikas.
You are welcome. Thank you.
Okay, our next speaker is Dr. Muhammad Anwar Nazir. He's from National Textile University, Faisalabad, and he's going to present his topic on double network composite hydrogel for sustained drug delivery applications. Yes, Dr. Muhammad Anwar Nazir.
Hello, can you hear me and see my slides?
Yes.
Okay.
You may proceed with sharing your screen.
Okay, so should I proceed?
Yes, please. Thank you.
Okay, thank you. So hello everybody. I am Dr. Anwar Nazir from National Textile University, and my topic of presentation is double network composite hydrogel for sustained drug delivery applications. So in this presentation, we will see a little bit introduction about the topic, problem statement, and some proposed solutions, methods and characterization of the materials, and at the end, the conclusions and some future aspects. If we talk about the tissue engineering, this is an interdisciplinary field of science that combines the principles of engineering, life sciences, to develop the biological substitutes that can ultimately restore, maintain, or improve the tissue function in the human body. So ideally, what we do, we take the cells from the human body, we cultivate them in 2D, and we seed the cells in 3D porous scaffolds. And these scaffolds are basically some engineered extracellular matrix having some growth factors, small molecules, some kind of nanoparticles, and cells. So after all these things, we get the organized tissue, and then we can implant this engineered tissue into the body back to restore or to maintain or the improve the tissue function. So this is overall the cycle of the tissue engineering and regenerative medicine working. So if we want to use the textile materials for tissue engineering applications, so what problems can we see? For example, one of them is the lack of bioactivity. So the textile materials are not actually bioactive materials. So what we can do, we can add some bioactive materials into the textile materials. And then, as we all know that the textile materials are macroporous structures. So we need to convert them to the microporous architectures. Why? Because there is one terminology that we call it as diffusion distance that should be the 100 to 200 micrometers for the cells. This is the distance between the adjacent cells in the tissues. So if the distance will be more, then it will be very difficult to transport the nutrients and to exchange the gases. So therefore, we cannot have the fully vascularized tissue by the end. So we need to reduce this proximity distance, and we can do this through some hydrogel incorporation. So these are some problems in the textile materials or the fabrication techniques right now, and we can have such kind of solutions to these problems. So drug delivery system, or DDS, is an application of the tissue engineering. And what we do in that one, we make the hydrogels. And these hydrogels can be made through physical cross-linking or some sort of chemical cross-linking. And these drug delivery systems have some stimuli. For example, if we have entrapped something into the hydrogel and we want to release that molecule or anything that is entrapped inside, we should have some stimulus or multiple stimuli. This can be the light, magnetic field, glucose levels in the body, shear stress, ultrasound, pH levels, electric field, enzymes, or the temperature, the change in temperature. So whenever we change the values of these stimuli, these drugs or these entrapped molecules can be released or just entrapped. So basically, the drug delivery system works in this way. So in this study, what we have done, we have taken the polyester fibers and we converted them to the non-woven fabrics through needle punching technique. That is very commonly known technique in textile engineering. On the other hand, we have taken the gelatin. The gelatin is naturally occurring material, and this is a bioactive material. So we took that material, we functionalized it with the methacrylic anhydride, and we ultimately obtained the methacrylated gelatin. So then now we have two different kinds of materials. One is the needle punched non-woven of the polyester fibers and the methacrylated gelatin material, bioactive material. So now we have prepared the solution of this gelma. We entrapped the drug. By the way, here we have taken the doxorubicin, an anti-cancer drug, as a model drug in this study. Then we added some photoinitiator and co-initiators. For example, in this study, we used the eosine Y, N-vinyl pyrrolidone, and triethanolamine as photoinitiator and co-initiators. We added them in the solution, and then we just poured the solution on top of this non-woven web. We exposed this non-woven web with the light, the visible light of wavelength 514 nanometers. And we converted this structure, the gelatin, to the cross-linked structure. So at the end of the day, we have the double network composite hydrogel having the polyester fibers and gelatin as a hydrogel. We characterized these materials also, and then we proceeded with the cytotoxicity of these scaffolds. So by the way, all these some methods we have already reported in the literature, but we just combined the textile materials and the techniques so to convert these materials to the useful products. So in this study, we developed basically 7 samples. So the first sample was gelma. We can call it as meth acrylated gelatin hydrogel. And then the second sample is the just non-woven of the polyester fibers, needle points non-woven polyester fibers with the GSM of 50, and then with the GSM 85, and then 110. And then we use these non-wovens, we combined this with the meth acrylated gelatin, and we obtained the composite hydrogel of gelma polyester with the different grammages, with the different GSM. So ultimately, we have the 7 samples. So of course, first of all, we had to see that whether we were able to incorporate this gelma or gelatin successfully into the fibrous network or not. So for this one, we performed the composition analysis through FTIR, and we can see that the amide region of gelatin is, of course, it's overlapped with the hydroxyl band, and we can see the appearance of this amide region over here. And the typical carboxyl peak or the carboxyl band of polyester is also appearing over here. So this shows ultimately that we have incorporated the gelma into the non-woven fibers successfully. We also analyzed the our scaffolds through scanning electron microscope, and we can see that we have the fibers and the gelma is also present over there. And as we are increasing the grammage of the our scaffolds, we are having the uniform distributed gelma all over the scaffold. And we can see that the double network in the form of the polyester fibers and the gelatin present in between the fibers, very fine distribution of these two. So the drug that we had entrapped in this one, we try to just monitor its release kinetics from these scaffolds. So when we were having the gelma hydrogel alone, we were having the fast release from the system. But as we are increasing the grammage of the non-woven fabric, like from 50 to 110, we can see that the release is controlled, or we can say that the sustained release is observed in case of composite hydrogel. So then we moved on to the cytotoxicity analysis. For this one, we performed the cell titer glow luminescent cell viability assay onto these scaffolds. For this one, of course, we took the gelma also alone, non-wovens, and then the composites one, because we wanted to show that, or we wanted to see that what happens with alone fibers and what happens after the incorporation of the gelatin into the matrices. So this is understood that when we are having the gelma, so we analyze, we seeded the cells. Of course, first we took the fibroblast cells, we seeded onto the scaffolds, we cultured them, and then on the day first, we analyzed how many cells are present. And then on day 4, we again analyzed that how many cells are present, like whether the cells were able to proliferate, to grow further or not. So in case of gelma, this is understood that from day 1 to day 4, we observed the significant increase in the number of cells. But as we were expecting that for just polyester non-wovens, there wasn't significant increase from the day 1 to day 4, because the polyester is also hydrophobic, and it doesn't have some, you can say that the attachment sites for the cells to attach and then further grow, because these cells cannot grow if they are not attached well. So they are adherent cells. But in case of 50 GSM composite, we observed an increase in the number of cells on the day 4, but this increase wasn't significant. When we moved on to the 85 GSM, we observed a significant increase in the number of cells on the day 4. And ultimately in 110 GSM, the JELMA was very uniformly present, and due to the presence of fibers also, the surface area was increased and the favorable environment was provided to the cells, and we ultimately observed the enhanced proliferation of the cells. So this ultimately show that without the incorporation of these bioactive molecules in simple textile substrates, we cannot use these for biomedical applications where the attachment of the cells, proliferation is very necessary. So we also try to visualize the cells in confocal imaging. So for this one, again, we seeded the NH3 fibroblast cells. There were 50,000 cells per well, and again in JELMA and 3 composites. So we can see that by the way, the red color is coming from the rhodamine, and it's showing the F actin of the cells or the cytoskeleton of the cells, and the blue color is coming from the DNA of the cells. So in case of JELMA, we can see the cells are present on the 3rd day, and in case of composites, we observe the similar pattern that we have seen for the CTG assay. So in conclusion, we can say that in this study, we have developed a sustained drug delivery system. And this study shows that textile materials and fabrication techniques also possess a potential for developing the scaffolds for tissue engineering and regenerative medicine applications. And potentially, we can use biostable and biodegradable scaffolds depending on the targeted application, if at a place we need the fast degradation, we can choose the appropriate materials. Of course, in future things, we have to go through the in vivo or preclinical and clinical trials for moving a step ahead towards the clinical translation of such kind of materials. But overall, this study shows a great potential for textile materials after some incorporation of the bioactive molecules, and even the techniques like weaving or non-woven substrates, even woven knitted substrates can be used for such kind of applications. So at the end, we would like to thank the ORIC of NTU for providing the financial assistance to complete this study. So this is all about my presentation. So if there is any question, then it's most welcome.
Thank you very much, Dr. Mohammad Anwar Nazir. Thank you for your insight on the topic of your research. Okay, our next speaker is. Oh, we have a question.
Okay.
Just hold on.
So mic permission.
Never mind, Dr. Anwar. Thank you very much. Okay. Our next speaker is Dr. Devita Amelia from University of Technology, Malaysia. The topic of their presentation is progress in polymer composites and their blends, encapsulation and encapsulation advanced technology for controlled release fertilizers. Dr. Devita.
Okay, thank you. Wait a minute. Okay.
Yes, we can see your slides. Thank you. You may proceed now.
Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. My name is Devita Amelia from University Technology Malaysia. and today I want to explain regarding progress in polymer composite and their blend encapsulation of fence technology for control release fertilizer. Outline of my presentation are introduction, problem statement, polymer-based control release, influencing factor, mechanism release, conclusion, and future challenge. The increasing human population poses the major global food security, and because of that, required an effective food production system to meet the food need of the ever-increasing human population. So, using fertilizer is a critical component in providing nutrients to increase the productivity of crops. Over 50% of the global population still consume food from the crop treated with synthetic fertilizer, but fertilizer application efficiency remains highly insufficient, where the effectiveness of the nitrogen fertilizer is 33%, the efficiency phosphor fertilizer is 24%, and the efficiency using potassium fertilizer is 42%. And then the synthetic fertilizer derived from the chemicals such as ammonia, natural gas, atmospheric nitrogen, phosphate mineral, and sulfur. But the weakness is around 70% of synthetic fertilizer are estimated to be lost to environment due to leaching, decomposition, nitrification, and polarization. On the other hand, inappropriate the chemical fertilizer application seriously impact the environment. Based on the report by the Department of Energy and Environment District of Columbia, synthetic fertilizer can release nitrous oxide, of which 1 pound of nitrous oxide has an impact of 3,000 times warming the climate compared to 1 pound of the carbon dioxide, and can remain in the atmosphere for over 100 years. In addition, global farmers apply approximately 115 million tons of nitrogen to crop yearly, of which about 75 million tons flow into the river, lake, and the environment. Because of that, to minimize nutrient loss in plant, increase crop yields, and reduce environmental hazard, control release fertilizer or CRF is alternative solution. Nutrient in CRF can be released efficiently and gradually adjusted to specific nutrient requirement during plant growth. And to produce the same amount of the production, CRF can reduce fertilizer utilization by 20 until 30%. Make it more efficient in terms of cost, labor, time, and energy. CRF can also reduce the toxicity cost to plant and increase the agronomic safety. But the most high efficiency fertilizer are not biodegradable. Because of that, the future demand of CRF formulation use a renewable biopolymer because environmentally friendly and sustainably without the production of the secondary pollution. 3 requirements that the CRF must fulfill. The first is less than 15% of the nutrients should be released in 24 hours. Second, less than the 75% should be released in 28 days. And the third, at least 75 should be released by the state release time, like 40 until 360 days. And the CRF innovation can be encapsulation or coated using organic or inorganic material to control the nutrient release pattern and duration according the type and the need of plant in their growth cycle. So the problem statement is the application of control release fertilizer in the field has yet not reached the optimum scale because the control release fertilizer encapsulation consists of the petroleum-based polymer. And material non-renewable resources like polystyrene, polysulfone, and polyvinyl chloride cannot be degraded into the soil and to form new type of the pollution later. So that the application of the biodegradable polymer matrix as alternative coating material which can minimize residue accumulation in the soil, such as the polylactic acid, polybutane adipate coterephthalate, PBAT, cellulose, lignin, and especially starch. Because starch have many advantages because it's low cost, ease of chemical modification, and their abundant availability. CRF mainly divided into coated and material type. The matrix are hydrophilic and hydrophobic, and the coated type divide into the organic and inorganic. Organic material can be sourced from natural polymer such as cellulose, starch, chitosan, gum, and so on. And synthetic polymer like polyethylene glycol, polylactic acid, polyurethane, and so on. This is several research related to biopolymer-based control release fertilizer. Sarma and Kakak use tapioca starch with additive acrylic acid, and MBA with fertilizer is urea, and fabrication technique is grafting. The performance is during 20 until 30 days, over 90 until 99% nitrogen release. And the second is Zafar, using polyvinyl alcohol with starch with additive acrylic acid, citric acid, and malic acid. Fabrication technique is fluidized bed. And then the performance is the spinach plant leaf production and uptake chlorophyll content and apparent nitrogen recovery all hinged by coated urea sample. And the ASIMI using PLA with additive is cellulose acetate. With fabrication technique is rotary press. The coating delay performance accomplishes the release rate required by European standard, but the adding cellulose acetate can decrease the crystallinity of the PLA. And sarcas using with starch with polyvinyl alcohol with additive is bentonite, and fertilizer is DAP. With fabrication technique is internal mixer. And then Da Silva using polymer PLA and PBAT with additive bentonite, fertilizer NPK, and using fabrication technique with fusion deposition modeling. The performance is filament containing bentonite release approximately 22% less fertilizer in 24 hours. And Scavaro have to research about fabrication technique, compression molding, and fusion deposition modeling. With using polymer matter B, and additive is natural fiber from Opuntia ficus indica, and fertilizer is NPK. And the last is Wang using polymer starch and PBAT with additive glycerol. With fertilizer is NPK, and fabrication technique is mud blending. The performance is rate yield increased significantly by 71.75%. Based on the Scavaro reported, the biocomposite using matter B and natural fiber from Opuntia ficus indica extruded by fusion deposition modeling is 3D printing is so the result the high porosity and the high mechanical strength. and OV fiber loading demonstrate control release and efficiency delivery of fertilizer in the water. Some factors that influence the CRF release. The first is temperature, because the temperature can control nutrient release, because the nutrient release can increase by lower temperature with microbially regulated fertilizer mineralization being reduced at low temperatures. The second is layer thickness. The resistance decreases as the layer gets thinner. This makes it easier for nutrient to be transported outside. On the other hand, the thickening the layer prolongs the release period and the lower the rate at which the nutrient compound diffuse out. The third is a binding agent. Binding agents such as stearic acid, citric acid, maleic acid, paraffin oil, and paraffin wax can be used to control the kinetic nutrient release. The addition of plasticizer can reduce water permeability. The important thing is effective coating can be achieved by combining different biopolymer or biopolymer with synthetic material through the blending or grafting or copolymerization technique, and so on. The fourth is hydrophobicity. Applying hydrophobic coating to control release fertilizer can regulate the rate of nutrient release and improve their efficiency and reduce the nutrient loss. And the fifth is polymer concentration and viscosity. Increasing the concentration of polymer in the coating solution can decrease the rate of nutrient release from the fertilizer granule. This is because the higher polymer concentration results in thicker and less porous coating layer that slow diffusion of the water and nutrient from the granule. However, if the viscosity of the coating solution is too low or too high, it can result in the incomplete or damaged coating, or even dissolution of the water-soluble fertilizer in the case of very viscosity. Therefore, its important thing is to carefully to control the concentration and the viscosity of the coating solution to ensure optimum coating thickness and porosity while avoiding the damage of the fertilizer. Overall nutrient release from CRF through the three main steps. Like the first is lag period, the second is consistent release, and the decay phase. For in the first step, the soil moisture main vapor moisten the crack on the coating surface and enter the coat. At this point, a small fraction of coated nutrients are dissolved, but no nutrient is released, as the only driving force in the vapor pressure gradient. At this stage, CRF based on hydrogel, absorb water, and swell. The present lag in this stage may be due to the time required to fill the internal space with the critical water volume or to establish a constant state between entering the water flux and leaving the solids flux. In the next step, more water continues to penetrate the core, which leads to the solubilization of more solid nutrient, increasing osmotic pressure and accumulation of the critical water volume of saturated solution, allowing the constant release of fertilizer through the coating pores or the swollen hydrogel network. Constant diffusion at this phase is due to the saturated concentration of the solution inside the granule. The important thing is the suppressing the pressure over a predominant level may result in the rupture of the coating polymer and instant burst release of nutrient content. In the last stage, most the nutrient is dissolved and the release decrease the concentration gradient and driving force, therefore the release rate. The sigmoidal release pattern is what matters in the fabrication of control release fertilizer as is refill nutrient release feature required for the plant. CRF biodegradation process in soil is the non-hydrogen forming biodegradable is hydrophobic coating and hydrogelling is hydrophilic coating. CRF with hydrophobic surface may have porous or non-porous coating. Porous hydrophobic coating such as the ethyl cellulose on the other hand follow the dissolution and diffusion mechanism for solid release into the water fill the pores. As the solid is depleted and change in void fraction and porosity may lead to increased release rate. The swelling and the shrinking event can create the crack or interstice the prompt surface erosion on the CRF. After nutrient release, the coating are left behind in the soil with low concentration of nutrient due to the difference in the concentration gradient, which release through biochemical disintegration. Erosion events such as in pH, water exposure, and photooxidation can increase the susceptibility of polymer surface to microbial attack. And the biodegradation of biodegradable polymer occur in the three steps. The first is biodeterioration, biofragmentation, and assimilation. So the conclusion is starch is very potential and versatile biomass for the coating material of control release fertilizer. Binder and filler play a vital and important role in the release pattern. Because they can form compact structure altering the properties of pore size and interacting with urea or fertilizer with vapor absorption. The material properties that make CRF sufficiently hydrophobic are critical for achieving control release without immediately disruption of the coating wall. The selection of particle dimension, fiber addition, and production technique are important factors that can modulate the fertilizer release rate. And the challenge is the first is the ideal control release fertilizer. We must design fertilizer formulation that suit plants' growth need and nutritional value requirement. For the material, we must define ineffective and abundant waste or biomass-based biopolymer such as starch and etc. And using less binding agent to produce dense composite structure with suitable release kinetic. And the third is about the 3D printing technology. We must can have the pores that are suitable for control release specific nutrient, and they use nanotechnology to enhance the problem of starch-based control release fertilizer. Okay, that's all my presentation. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikum Assalam. Thank you, Dr. Divita Amelia. It was a very nice presentation. Thank you for sharing your insights with us in this conference. So far, we don't have any question yet. So we will move to our next speaker.
Our next speaker is Dr. Faiza Rashid from Quaid-e-Azam University, Islamabad. She will present her work on investigating PABA modified cellulose nanofibers for superior bioplastic attributes. Dr. Faiza Rashid, please.
Assalamualaikum everyone. I'm just trying to share my screen with you. Well, just give me a minute. I could see it here, but I just can't hear it.
Okay, take your time. The share button is right next to the
Yeah,
leaf.
I can. Yeah. I have the share button and I'm trying it from my window, but I can't see my presentation on window. So that's very strange because we just did it for Dr. Vakas, and right now it's just my presentation is not appearing in the window pane. I don't know. Okay, at the moment I'm sharing my entire screen and then I will open my presentation. Maybe, can you see my presentation now? Yeah,
Just
okay.
hold on. Cannot see. Yes, we can see it now.
Yeah, so I will be talking about investigating para-aminobenzoic acid modified cellulose nanofibers, which we are looking for superior bioplastics attributes. I'm Dr. Faisalabad and I work as assistant professor at Qaid-e-Azam University, Islamabad. My main research focus is on alternative biopolymers instead of synthetic plastic-based polymers. And we all know that fossil fuel drive plastics, they have paved an important place in our life because they offer some very, exceptional utilization or exceptional properties. For example, they are versatile. We can produce a lot different types of materials from fossil-based plastics. They are protective. All the contents that we store inside these plastic-based materials, they keep them protective for a longer period of time, and all the equipment or any machines that we make from these plastics, they are very protective for a longer period of time. They are very convenient since they are light in weight, comparatively lighter in weight compared to metals. And they can be easily molded into different types of shapes. They can be used as safe for electricity equipments and many other things. And they also are very easier to transport and they help in logistics. So we find nearly plastics in every second product that we are using. So if you all where you are sitting right now, if you take a look into your room, you will find a lot of different types of plastic materials in the room, and they all are made in different shapes and they are molded into different types of things. And this is what they have, why they have made an important place in our daily life. But with all this importance in our life, they do come with the baggage, and that is that they have put a lot of threats to our ecosystem, to our environment, to our aquatic and terrestrial life forms. And in this presentation, I will talk about different kind of alternatives that we can use instead of these plastic materials. So before getting into the detail, I will just like to show you a couple of examples. So in this slide, you will see this poor creature turtle that has been entangled into a fish net. So this is made up of plastic, and of course he have no place now to go anywhere, and he's completely entangled in this one. So this is where it has made some threats to our marine life. In the second picture, you see a sperm whale, and you see its open stomach. So this sperm whale has been caught dead at the shore of Spain or Italy in 2019. And when its stomach has been examined, about 64 pounds of plastic debris has been discovered, which has been associated to the cause of its death. So these plastics, though they are very versatile and they are very convenient for our use, they do have some kind of drawbacks. They could also end up in food chain as microplastics. They can pollute our drinking water resources. They have resulted into loss of biodiversity due to these kind of incidents that I have just shown you. And of course, the economic impact is also bad in some terms. Well, they are cheaper, for example, compared to their bio-based alternatives, but the environmental footprint is really bad for these plastics. So the cost that we are saving now in order to make a biodegradable alternative, we will be spending it later on in terms of saving our environment. And we have seen some worst examples in our previous years. For example, this flood that has been a bigger reason of this flood that we had in Pakistan last year was associated associated to climate change, and then climate change is directly or indirectly associated to the extensive use of fossil fuel resources. So in one or other way, we have to reduce our dependency on these fossil fuel-based plastics, or overall on the fossil fuel-based products. So these kind of events or these kind of situations have raised some kind of awareness or environmental awareness in our population, and we are looking for some sustainable alternatives. There are also regulatory pressures from different governments on several in several countries or even several continents. For example, in Africa, they have restricted the use of plastics. We also had seen these kind of practices sometimes in Pakistan as well, and in Europe, of course, we are having a lot of renewable plastic resources now. We are also having green energy resources in several advanced countries. So of course there are regulatory pressures which tend us to move towards sustainable alternatives. Then of course now we have a lot of technological advancements which are giving us more opportunities to make biodegradable alternatives to synthetic plastics. And then there are business benefits as well, because with the use of bioplastic, we may raise the economical value of crops, which can directly benefit the farmers as well as other end users or the stakeholders which are involved in the chain. So therefore, I think this sustainable plastic need is very much enlightened in the public as well. I am showing two examples. If you see on this slide, these two pictures, they show some kind of renewable plastic materials. In the first picture, we have a rice bag which has been, and the rice are being packed into a renewable packaging, which the packet is made from starch. And when you will boil the rice, you will boil the packet as well, and you will eat your package along with your product. In the second picture, these are coffee cups that have been introduced by KFC, and these coffee cups are actually cookie cups with an insulating chocolate layer inside. So you will first drink your coffee, and then instead of throwing your cup, you can eat it as a cookie. So this is just an example of the traditional packaging material which are edible, ice cream cones. So we have seen ice cream cones as edible packaging materials which we don't throw but we eat them. So these coffee cups are introduced on the similar concept. So these are certain examples where we can see that we can replace these plastic materials in some of the applications. These are some packaging materials or some plastic materials which we have produced in our lab. This round film is made from wheat proteins. Then we have different sheets with different colors which have also been produced with wheat proteins, and the dyes that have been used inside these films, they are also from renewable resources. Then we have this tray with different commodities inside. This tray is also made from wheat proteins. So we can see that these plastics, these renewable plastics or renewable polymers from plants, they can also be molded into different shapes like the other synthetic polymers. Then we have a shiny sheet here, which is also from wheat proteins. And then we have coated it with some kind of materials to make it more resistant to microbes or mold growth. And in this one, you see more extruded materials which are being made from polyhydroxy alkanoids and wheat composites. So with these examples, we can see that the renewable polymers, they can also be molded into different types of materials, and we can safely replace some of the synthetic materials with these materials. These sheets, they're also printable, so we can make some printing on them as well. One of the alternate that we can introduce instead of polyethylene or polypropylene based plastics are wheat gluten proteins, which are one of the largest polymers in nature, and they have shown some very you can say exceptional properties. For example, they are cohesive in nature, they are elastic, you can extend them up to 400%. They have shown excellent gas barrier properties, which are important when we are looking for the packaging materials. And these wheat gluten proteins, they are also available in bulk quantities, as they are a co-product from starch and bioethanol industries, and they are readily available as a demonstrative material for packaging applications. In Europe, about 100,000 tons of wheat gluten is produced annually as a result of byproduct from starch and bioethanol industries. So this product doesn't go into any kind of value-added product formation, but it is being used as animal feed. So in this study, we have demonstrated some kind of value-added utilization for these proteins, and they have been successfully molded into different type of materials. In this study, the basic objective of this study was these materials that I have shown you in these slides, they demonstrated some excellent properties. For example, I have just said that they have excellent gas barrier properties, they are cohesive, they are elastic, but they suffer from poor strength compared to their synthetic polymeric materials, for example, polyethylene or polypropylene. So to make them compatible, we need some kind of additives or some kind of fillers in these materials. And we, in this study, we plan to have these fillers as well as from renewable resources. So in this one, we have used cellulose nanofibers as the fillers. And in our studies, we like to use waste resources and we want to get some valuable products from waste. So these cellulose nanofibers, they have also been produced from wood waste, for example, sugarcane bagasse, or eucalyptus bark, which have been dead over the period of years and have been eliminated from the tree. So these two sources of cellulose nanofibers have been used to produce cellulose nanofibers by using different chemomechanical methods. And then in second part, we did some functional modifications to cellulose nanofibers, which were about para-aminobenzoic acid based modifications, and then we also did some microwave assisted modifications to these cellulose nanofibers. And then we used these cellulose nanofibers as fillers to wheat gluten. We use both modified cellulose nanofibers, which have been produced through functional modifications of CNF, and we have also used the normal cellulose nanofibers that have been directly extracted from eucalyptus and sugarcane bagasse. So in this biocomposite formation, we used wheat gluten, we used cellulose nanofibers, we used modified cellulose nanofibers, and we also did some film coating. I'm not getting into details about cellulose nanofibers because I have seen before, I think, lunch break, a colleague of mine from Malaysia, Dr. I think Amreen Chaudhary, she very well established the background for the nanofibers or cellulose nanofibers. I'm not getting into details. So you know that the cellulose nanofibers, they are very strong. If they have been fabricated correctly, they can offer you a stiffness as compared to steel. So they are very important when we are using them as fillers to like proteins or other biopolymers, for example, starch. So we have produced some kind of materials from these cellulose nanofibers and proteins. This is the methodology. First, we extracted cellulose nanofibers, as I explained in previous style. Then we did modification, and after that, we did composite formation by using compression molding technique. This is the scheme for the extraction of cellulose nanofibers, and the scheme, and in this extraction process, we tried to keep it as simple as possible so it can be upscaled at the industrial scale. So it was just this sample washing. If we have taken eucalyptus bark or if we have taken sugarcane bagasse, then we dried the material. We did grinding, dewaxing of material, and alkaline treatment. Then acid hydrolysis, sonication, drying, and storage. This scheme is not as complicated as the schemes that have been presented in literature. So we tried to optimize the process in terms of cost as much as possible. This is in detail that how we have continued this process in the lab. I will not get into details. So if someone have any question, they can ask me later. But here in the last slide, you can see different types of cellulose nanofibers that we have produced starting from this eucalyptus bark material. Later on, these cellulose nanofibers that have been produced in this slide, they have been functionally modified by esterification reaction by reacting them with para-aminobenzoic acid. So in the para-aminobenzoic acid and cellulose nanofibers, they have been reacted together, and the cellulose nanofibers hydroxyl group, which we can see here, they react with the acylating chemical here in the para-aminobenzoic acid, and we were able to release this water molecule, and these two molecules, they were able to bond with each other, and the cellulose nanofibers, they get here a new functional group from this PABA molecule. This PABA modification also made the cellulose nanofiber more, or they were able to retain the crystal structure of cellulose nanofibers. And this crystal structure make them very functional in terms of that it remains insoluble in organic solvents as well as in water at room temperature, which affects the hydrophobicity of cellulose nanofibers, making them more hydrophobic and less and with high barrier properties to different kinds of moisture environment, which are very important for the material application. So these are the cellulose nanofibers from bagasse that we have modified with different chemicals. They could be modified with para-aminobenzoic acid, and they can also be modified with toluene, sulfuric acid, and also with cellulose nanofibers. These two kinds of cellulose nanofibers, they can be combined with each other to form a novel type of cellulose nanofiber. I will discuss only the cellulose nanofiber that we have modified with para-aminobenzoic acid in this talk. So this is the scheme of the modification of cellulose nanofibers that we have obtained in the previous experiments, and then they have gone through different types of processes, and in the end we were able to have the modified cellulose nanofibers, which you can see here. Later on, these cellulose nanofibers, they were used for the formation of composites with wheat gluten proteins, which are one of the largest polymers in nature, and they can make a very well-defined matrix for the incorporation of cellulose nanofibers. This is the compression molding instrument that we kind of manufactured, tailored manufacture for our lab, and we did the film formation with this equipment. We use 70% gluten proteins, 30% glycerol, and then we use very variable amount of nanofibers, both as cellulose nanofibers and modified cellulose nanofibers. We use 5%, 10%, and 15% of these fibers in the composite formation, and they have undergone through heat and pressure for the manufacturing into film. These are different types of films that we produce from the first film is only the wheat gluten glycerol film. In the second film, we have cellulose nanofibers, and in third film we have modified cellulose nanofibers. In the table, we have given the details at how these samples have been manufactured. So in first one, we have only gluten and glycerol. In the second one, we have gluten, glycerol, and cellulose nanofibers. And in third one, we have gluten, glycerol, cellulose nanofibers, and modified cellulose nanofibers. Then to make them more resistant to microbes or mold growth, because they are going to be used in open environment, we did surface coatings of the films. For this, we have used chitosan, which had good antimicrobial properties, and we dissolved chitosan in dilute acetic acid, so the surface structure is not damaged. And then we also did we added salicylic acid, and both of these solutions, they were combined or homogenized together, and then we did a coating, and they have been dried afterwards. After coating, we did characterization of our films and also the different types of cellulose nanofibers that we have produced. In this slide, I have shown the results about the characterization of cellulose nanofibers. When we produce cellulose nanofibers, we did FTIR analysis to see that it is showing the characteristic structural peaks, and we are sure that the cellulose nanofibers have been formed. So these are characteristic structural peaks that we were able to identify in FTIR charts. Then we also did zeta sizer analysis. So we know that the structure or the cellulose nanofibers, they are only in uniform size, and there are no additional groups which are present, and that has been verified by zeta sizer analysis. We have also looked into the zeta potential. So when the zeta potential is on the negative side, that means the cellulose nanofibers that we have produced, they are stable in structure. And in scanning electron microscopy, we were also able to see the fibers in these materials. We also characterize the modified cellulose nanofibers by the same techniques, and we see additional additional peaks in FTIR analysis, which were indicating that the cellulose nanofibers, they have been successfully modified by acylation reaction. We have also seen an increase in size compared to the unmodified cellulose nanofibers, showing that the attachment of the heavy functional group on the side chain of cellulose nanofibers, and the zeta potential was also reduced, showing this increase, you can say increased stability of the cellulose nanofiber, modified cellulose nanofibers in solution. The UV analysis also confirmed the presence of amino-benzoic acid in the cellulose nanofibers, which indicated the successful modification of cellulose nanofibers. The SEM analysis was also done for unmodified cellulose nanofiber, and on the right side we can see that there have been bulky groups that were obvious on the cellulose nanofibers. So here we see a loose structure of cellulose nanofibers in this one, which is for unmodified cellulose nanofibers, and here we see bulky structures, or we can say a compact structure of modified cellulose nanofibers. So we had very successful modification of cellulose nanofibers. Yeah. We also did some solubility testing, and we see that with modified cellulose nanofibers, we had high amount of insoluble proteins showing the compact structure of these fibers. We did antimicrobial analysis to see that they are resistant to the growth of microbes, and we see the clear zones on the cellulose-based films. So this shows that they are resistant to microbial growth if we use them for packaging applications. So in conclusion, we can say that this study advances our knowledge that how we can use these nanomaterial modifications for the promising solutions in different types of materials which are derived from biodegradable polymers, and they can offer us some kind of sustainable alternatives to the synthetic materials which we use very often in our environment, and they are of course not very good for the environment. So I think with this, I would like to thank you all for your attention to the presentation, and you're welcome if you have any questions. Thank you.
Thank you very much, Dr. Faiza, for presenting your topic. It was very informative for all of us. With this, I would like to thank all our keynote speakers, our attendees, and as well as all the speakers who participated in today's session. With this, today, I will conclude this session, and inshallah, tomorrow we will start our day 2 session 1 at 9:30 Pakistan time. Thank you very much for joining in on us on our 3rd International Conference on Polymers and Composites. Thank you again. Allah Hafiz.